Hello everyone, I'm Xiayu from the University of Illinois at Champaign. I'm a PhD student supervised by Dr. Houtan Jebelli. So unfortunately, due to my visa processing delay, I was not able to travel to Canada and join you in person today. I am sorry for that and appreciate your understanding. So today I'll be presenting our work on sensor fusion and hierarchical inspection strategy for aerial ground multi-robot system. So this work addresses the critical need for efficient and comprehensive infrastructure inspection through robotic collaboration. Let's start by looking at the challenges we face in inspection tasks. There is a growing demand for inspecting aging infrastructure, but many areas are hard to reach or dangerous for humans. Current methods have limitations. For example, manual assessment is inefficient and costly. Fixed sensor systems need manual setup and don't work well in high-risk areas. Robotic systems offer advantages. They are safer, more precise, and cost-efficient, but they also have limitations we need to solve. Let's examine these limitations more closely. Aerial platforms like drones provide rapid coverage, but suffer from limited battery life and can only capture distant views. Ground robots offer detailed inspection capabilities, but have restricted mobility and risk damaging structures. Both platforms have limited perception when operating independently. To sum up the knowledge gap, it is the single-function robotic platforms are insufficient for autonomous inspection. So this gap in current technology led us to develop an integrated aero-ground system that leverage the strengths of both platforms. Our solution consists of two main components working in harmony. The aerial module uses a hexacopter equipped with LiDAR, 4K RGB camera, and thermal imaging for rapid site mapping. The ground module includes two specialized robots, a hexapod robot capable of navigating 30-degree inclines, and a tracked robot with 0.1 mm crack detection resolution. So the system operates in two phases. First, initial aerial survey, and then followed by targeted ground inspection. A key innovation is our sensor fusion framework. We synchronized data collection across all platforms with a millisecond accuracy. The system extracts features from visual, thermal, and LiDAR data, calculating confidence score for each modality. Using extended Kalman Filter and ICP algorithms, we achieve precise alignment of sensor data with 0.7 mm registration accuracy. Our path planning framework implements three levels of intelligence. Global planning optimizes energy, time, and risk costs across the entire inspection area. Local navigation uses enhanced RT star for real-time obstacle avoidance. Most importantly, the system adapts through Q-learning, continuously improving its inspection strategies based on accumulated experience. For our experiments, as you can see, we have a comprehensive system with multiple components working together. We use the WeBot simulation platform, which allows us to test in different terrain conditions before implementing the system in real-world settings. So the system includes navigation modules that process information from sensors through an extended Kalman filter. And our setup includes a controller board for processing, various scanning sensors, and Wi-Fi communication between the UAV and the UGV. We tested the system on different types of terrain that match our two test scenarios. The results demonstrate great performance across all metrics. Our area mapping achieved 127 points per square meter density with more than 96% feature extraction accuracy. The sensor fusion framework maintained millimeter registration errors. Notably, the system achieved 99% collision-free operation while responding to anomalies in just 3 seconds. To conclude, we have successfully developed a hierarchical multi-robot inspection system that addresses fundamental challenges in infrastructure assessment. Our 3 main contributions are transformative for this field. First, our aero-ground robot combination overcomes the coverage versus detail limitation of single platform systems. The aero module provides rapid site mapping, while ground robots deliver millimeter precision inspection where needed. Second, our advanced sensor fusion framework achieved millimeter accuracy by intelligently combining visual, thermal, and LiDAR data. This multi-modal integration enables detection of complex defects. Third, our adaptive coordination strategy using Q-learning allows the system to improve with experience, optimizing inspection paths and resources allocation in real time. We acknowledge important limitations. Environmental conditions can affect sensor performance, and the computational requirements are substantial, and our validation is currently simulation-based. So these challenges guide our future research directions. Moving forward, we will integrate deep reinforcement learning for enhanced decision-making and develop noise-robust fusion algorithms, and most critically, conduct some real-world validation on actual bridges and industrial facilities. And here are our key references. I'd like to particularly acknowledge the fundamental work in robotic inspection systems and sensor fusion that informed our approach. At the end, thanks for all your attention. I'm happy to take any question or get connected via my linking. Please feel free to reach out. Besides, I'd like to express my sincere gratitude to the ISARC conference organizers. Also, thanks to our funding agencies, my PhD advisor, Dr. Jebelli, and all the members of the RACE Lab. Thank you all.